Okay, where are other boys? What happened? Where are other boys? Where are other boys, guys? Is this chemistry period? Physics period? Yes, boys. Chemistry or physics? So, do you hear me? Do you hear me? Hello?
Yes, sir.
This is physics period, right?
Yes, sir.
Where are students?
Sir, I don't know. They are joining slowly.
Will take the first period.
Sir Zia.
He will leave the class on time.
Yeah, but some boys they join late.
Salam.
Morning.
Right. Around.
So can you explain that question we were doing yesterday?
Yes. Sorry. So today we will not waste our time because yesterday we have. Okay. So we were doing sample paper.
So the last thing I remember was we were doing binding energy. So
Binding energy. Okay. Just let me check. Four. This. 5.
so up.
Is this the one?
Yeah.
Is meant by the binding energy of a nucleus, right?
Okay.
So calculate the binding energy of a nucleus.
So because sometimes we have to divide by the number of nucleons, right? So when do we use that concept?
Nucleon. Yeah. So binding energy of a tritium nucleus. So you have to see, because there are 2 protons and 1 neutron. So 2 proton mass and plus 1 proton mass. Just add them up. Subtract with the mass of the nucleus. So mass of the nucleons minus mass of the nucleus. Because mass of the nucleus is smaller than the mass of the nucleon, just subtract them up, and then you will get the mass difference. Mass difference multiplied by 1u. Mass difference multiplied by 1u. So this will be, mass will be converted into kilograms. So once the mass is in kilogram, then you can use delta E equals to delta mc square to get the energy in joules, and then divide by the electronic charge. 1.6 × 10 power minus 11. Forget this number. 1.6 × 10 power minus 11, and then this will be converted into electron volt, then mega electron volt. The long procedure. So try not to use that 9. What was that? 90.
931.5.
931.5 mega electron volt. But you can get the answer directly using that concept. Okay. When massive nuclei undergo fusion, the binding energy per nucleon decreases actually. So you have to supply energy in order to this fusion reaction to go on. So you have to supply energy. Yes. What was your question?
Since some questions they divide our value with the nucleon number, and in some questions they don't. So when should we do that?
Yeah. So when we need the binding energy per nucleon, then you have to divide. If they just ask binding energy, like in this question, they're just asking about the binding energy. So you don't need to divide,
Okay, sir.
right? But there are some binding energy per nucleon, then you got to.
Okay, sir. Thank you.
The luminosity of the sun, so calculate the radius of the sun. So this is already discussed, because whenever there is a question about luminosity, there would be a question about intensity as well, radiation flux. So this is a question about radiation flux, and this is luminosity. So luminosity formula, you already know the luminosity
Sigma
formula
18.
is this, so you can calculate radius, and radiation flux formula is this. This is intensity formula, and plus there is another intensity formula of power over area. So it is the same as this one. So you can calculate power equals to I times A. The only issue was the efficiency concept, so we have skipped this thing, that why they have used this thing. This you can understand by just going over this question two, 3 times, so you will understand this thing. Okay, so we have skipped for the time being in order to save time. But whenever there's a question about luminosity, there would be a related question about the intensity of the waves, intensity of the sun. The problem here is that in this question, they did not mention the word intensity. Did they mention the word intensity here? No. Did they mention the word radiation flux here? No. They didn't mention intensity. They didn't mention radiation flux at all. How do we come to know that which formula shall we go for? So you see this is a question about luminosity. So with the luminosity, this formula is attached, intensity. So the second part would be about intensity, most probably intensity. So intensity
because
is power
they give
over
the
area.
area, so I think we just have to assume that we should use.
Yeah, you just have to assume, because the area is given, so you can assume that. Wait. So you can assume that this is about intensity. In November 1940, the wind caused. Okay, so this is Tacoma Bridge. Tacoma Bridge narrows in the United States. The amplitude of the oscillations became so large that the bridge collapsed. Name the effect that caused the bridge to oscillate with increasing amplitude. So resonance. It's a resonance. The vertical oscillation of the bridge can be modeled using the equation of circular motion. Calculate the maximum acceleration of the bridge when it is oscillating 38 times per minute and the amplitude of oscillation is 0.9 meters. So you have to calculate the acceleration, maximum acceleration. The formula is minus omega square x. This formula is given in the formula sheet. Maximum acceleration. Let me show you the formula sheet today, because students they should know that they should know how to use a formula sheet. So this is the formula sheet, and let's see the maximum acceleration formula. So maximum acceleration formula is given or not. So maximum acceleration is equal to minus w square x. So this is the formula, minus w square x. So this formula is given, so we have to use this formula. This formula, the second formula is hardly used. Second or third formula is hardly used. Most of the time it's the first formula or the fourth formula that is used, the displacement formula. Second and third formulas are hardly used. So A equals to minus w square x. So we have to go for this thing, A equals to minus w square x. Right, so you can calculate the maximum acceleration, A equals to minus w square x. So we need w, right? W equals to 2 pi x.
Divided by 60 into 38. So.
Yeah. So this is 38 times per minute. So 38 divided by 60. So this would be 38. 38 divided by 60. So this would be frequency, because per second. So this would become frequency. You can calculate frequency, then 2 pi f. You will calculate w, and the amplitude is given in meters. So minus w square x. So you can calculate maximum acceleration. Why 4 marks? Why 4 marks? For what?
14.3 is the answer I'm getting.
Yeah, 14.3 is the answer. So why 4 marks are given for this?
Each step gives a mark.
Steps. Frequency is 1 upon time period, but the best formula is this n, the number of times, number upon the time, not the time period. So this is the best formula that we should quote. But we use what we have studied in grade 10, 1 upon t, the inverse of time period. Okay, so you will keep on using that formula. You don't have to rely on this. Obviously, when the number is given 38, right? 38 number, and time is 60 seconds. So it's okay, it's given. This is time period.
Question, sir.
Yeah, so this is the question. So whenever it was oscillating 38 times per minute and the amplitude of oscillation is 0.9 meters, so you can calculate maximum acceleration. This is a very simple question.
Sir, but could you show the mark system again? I just joined late, sir.
Yeah, so if you calculate the maximum acceleration, so frequency is given. Frequency is like 38 times per minute. 38 times per minute, so 38 divided by 60, so this would give us a frequency. 38 divided by 60, this would give us a frequency per second, because we have converted this into seconds. And then W equals to 2 pi f to calculate W. Once W is known, then acceleration equals to minus W square x. This formula, you will find it here.
It's in the data
Acceleration
booklet, sir.
in the formula sheet. So this formula is here. Second and third formulas are not important. Fourth formula is important. And W equals to 2 pi f is given here. Okay.
Yes, sir, I got this. Thank you, sir.
And we'll come. Complete a free body force diagram for a car in contact with the road surface of the bridge. As the amplitude of the vertical oscillation increased, people left the bridge, leaving their cars behind. So I'll show you how did the people leave their car behind. So this is called resonance bridges. So you can see that this is the Tacoma Bridge. This was broken in 1940. Okay, this is in United States, so this was broken. I've shown you the video as well. So the people have left their cars behind. So this is the car. The people have left their cars behind, right? This is the car.
Yes, sir.
And this is the mad professor. Okay, so what would be the free body force diagram? So obviously the contact force acting upward and the weight acting downward. So this would be the free body force diagram. Assess the validity of the suggestion that at certain points in the oscillation of the bridge, any car would lose contact with the road. Okay. So this is the question. Assess the validity of suggestion that at certain points in the oscillation of the bridge, any car would lose contact with the road. Okay. So two forces are acting. So one of the force is acting upward. So this is the reaction force. Another force is acting downward. So this is the weight. So these two forces are acting. Okay. So weight is acting downwards, and reaction force is acting upward. Right. And we have a car over here. Right, so two forces are acting on the car. So reaction force and weight. Now this car is obviously oscillating up and down. So this car is oscillating up and down. Right. So this is the equilibrium position. Let's say this is the equilibrium position of the car. So it is oscillating up and down. Now so this is the equilibrium position. So you can write that this is the equilibrium position, EQ. Okay, so the car is oscillating around this equilibrium position, right? So according to Newton's second law, F equals to ma. F equals to ma. Oh. F equals to ma. So, okay, acceleration of the car. And this is the resultant force, right? So this is the resultant force, RF, resultant force. So it could be R minus W or W minus R. I'm not sure for the time being it's R minus W or W minus R. Let's think that it is W minus R. This is given in the notes, so you can go over the notes. It's W minus R or R minus W. So equals to MA. And then W equals to mg. So I can rearrange this formula. This is also given in the notes, so that R equals to m and then bracket and then g minus a. So you can rearrange this equation and you can write this equation into this form, m into g minus a, right? So you can write it in this form. Now they're saying would lose contact. Anything that lose contact, its R is 0. Its R is 0. So R is 0, right? We have learned this in oscillation chapter that there's R is 0 if it loses contact. So we write 0 here equals to M times G minus A. And then you can, you can write it in another way. You can write it as mg minus ma. Okay, mg minus ma or mg, so you can bring ma on to the left side. So mg would be equals to ma. This is also done in the oscillation chapter. Same stuff is done already. So get cancelled. So a equals to g. So acceleration equals to g. So whenever acceleration, so whenever it will lose context, obviously it will fall into the waters, right? It will fall into the sea, river. It will fall then into the sea or river, whatever. So it will fall, right? So when it will fall, its acceleration would be g then, right? Because whenever the bridge will collapse, the car will go down, right? So its acceleration would be equal to g. So the bridge is collapsed and the cars are going down into the sea. So its acceleration is equal to g. So this is what we have to prove here. So this was slightly tricky question, but like if you see this lose contact, and if you just go back to the theory, so you can understand that it's about this thing. Okay. So R and weight, and this is what you have to do here. So yeah, it is W minus R. So you can make R equals to this, and then when R equals to 0, so acceleration equals to G or greater than G. Okay. Greater than G because some other force is also acting, might be acting, but it would be equal to G. Okay. The photograph shows a battery-powered toy that floats on a cushion of air over any smooth, flat surface. This is the top view, this is the side view. A fan expels air from underneath the toy, so the air is expelled from here, allowing the toy to float a few millimeters above the surface, so it will hover in the air, ensuring that the toy can move freely. Explain how the action of the fan allows the toys to float a small distance above the surface. So you have to use Newton's third law, obviously here. You have to use Newton's third law. Because the air is pushing the surface down. Sorry.
So the fan is producing a force downwards.
Fan is producing a force downwards, or it's between air. So we have to identify two bodies, right? One of the body is air. The other one is the
surface.
The surface. So if air is hitting the surface, so how come the surface will hit the air? So we have to identify two bodies. Once you have identified those two bodies, like then you have to apply action and reaction. So that's why it floats. So and then one mark is for writing that word resultant force. Resultant force is acting on this toy. So due to Newton's second law, resultant force is acting on this toy. So one mark is for writing the word resultant force. So air is pushing against the surface. Let's say surface is the second body. Then the surface pushes the air up. It is the toy and the air. So the toy is pushing the air down. So air is pushing the toy up. So it's just like rocket. You remember rocket example? So in rocket example also we were saying surface. It was not surface. The rocket pushes the air down. So air pushes the rocket up. So it's the same thing. So the toy pushes the air down. So air pushes the toy up. Okay, and then there is a resultant force on the toy. And this is Newton's third law. So different forces act on different bodies. Blah blah blah. So the fan in the toy pushes the air molecules downwards. So you see, just like a rocket. So we're right. The fan in the toy pushes the air molecules downward. So the toy pushes the air. Toy pushes the air. Actually, it is toy pushes the air downwards. When the cellular toy is pushed. Okay, fine. And see this balances the weight of the toy. This is the resultant force. This is the resultant force, and we forgot to say that it balances the weight of the toy. We forgot to say this thing. Okay, so it is balancing the weight of the toy. That's why it floats. A teacher uses two of the toys, A and B, in a demonstration. Toy A moves towards toy B, which is initially stationary. The two toys collide. The teacher states applying Newton's second law and third laws of motion to this collision leads to the conclusion that momentum is conserved. Justify this statement. Wow. Okay, this is momentum conservation, so it's easy, so we can just see this. Guess this. So we have to write about the momentum conservation. Toy exerts a force on toy B and vice versa. Force is equal in magnet opposite direction. Forces act for same time. So this is applied in the second law. Total momentum change equal to 0, so momentum is conserved. For another toy, so momentum is conserved. And impulse equation. So all these points you can write. But why these points? Okay. So you see this thing, they have given that applying Newton's second law and third law. So we have to apply these two laws only. Okay, to this collision leads to the conclusion that momentum is conserved. Okay, so when it's given that you have to apply these two laws only, okay, so it's given that you have to apply these two laws only. So you know that action is equals to reaction, right?
Yes, sir.
So force that body A applies on body B is equal to the force applied by body B on body A. So you will start with this. Right, so this is Newton's third law, and with minus signs, you will start with this, right? And a force equals to rate of change of momentum. Right, so this equals to rate of change of momentum. So this would be m VB minus VA. But where are we going with this thing? Divided by the time. Where are we going with this thing? Because the equation for this would also be the same. Only you have to write VA minus VB. Where are we going with this thing? Mass of what? Like similar approach you have to follow, but like this will cancel because these two are equal. This will cancel. So forces are equal. Obviously, you have to use this. We have to prove that the momentum is conserved. So you have to use the same concept.
Because isn't the momentum of B 0 initially?
Shall we use the momentum formula?
Yes, sir.
Because they are using second law and third law only. Otherwise, we can use the momentum formula. Like mostly students will go for this thing only. They would use the momentum formula. They would say that momentum of this is 0 and momentum of this is mv. Let's say mv. So this is 0, and then after collision, these two stick together or not? The two twice collide, and it's not given that these two stick together. So they would try to use a momentum conservation. But I am trying to do it like differently because they are asking for Newton's second law and third law only. So I'm not just going for that thing. So I'm just trying to do it this way. Or let's do Newton's second law. So F equals to ma. F equals to ma. So because their masses are not given, their velocities are not given, so how can we use law of conservation of momentum? So m into VB minus VA, so this would be acceleration. VB minus VA. This is their acceleration. All over the time during which this collision happens, right? So we can write it this way. So this is equals to force, and right. So this is equals to force. So this T will be multiplied with this one. So F into T. F into T equals to change of momentum. So VB minus VA. So that's how we can get impulse. So this is what we can do, because if we go for conservation of momentum, we don't have the values. We don't have any data with us. So this is what we can do. So impulse equals to change of momentum.
So in this mark, they just gave half the marks for just stating Newton's third law.
Yeah, maybe 1 mark for stating Newton's second law.
So they gave 3 marks for stating third law.
So apply Newton's third law. So we applied the Newton's third law. Force is equal in magnitude and opposite in direction. So 2 marks. Oh,
so 3 marks also
at for same time. 3 marks for writing this thing. 3 marks for writing
third law is half the marks.
So 3 marks for writing this thing. So just this equation, if we write, so it means 3 marks. Wow, because the forces are opposite, minus sign. Forces act for same time. Okay. Actually, this question was asked a couple of times in the past. So what they do, I forgot that method. So this is about action and reaction, and then the impulse applied by A on B is equal to impulse applied by B on A. Yeah, this was different. Impulse applied by B on A. This is the one, B on A. So this is another equation that you have not studied. That impulse applied by, so question of impulses are slightly tricky. We just ignore questions from impulse. So it is like force multiplied by time for AB is equals to force multiplied by time for BA. Like the impulse applied by toy A on toy B is equals to the impulse applied by toy B on toy A. It is equal, provided the time is equal. So 1 mark for writing that the time is equal. So this is what we have to write. So these 2 equations are enough. These 2 equations we have to write. So 3 marks for this, and probably we have to write something about this equation. So can we prove this that momentum is conserved from this equation? From this equation, we cannot prove momentum is conserved, because but from this equation we can prove that momentum is conserved. F equals to ma. We can find the equation for momentum. But like from this equation, can you prove the momentum is conserved? So forces are equal. Okay, time is also equal. I forgot that. Like it was asked in the past couple of times. I forgot the working. Okay, so I would include this in the notes. So whenever you get the notes, so you will find this thing. So you find this question. Okay. Let's skip this for the moment, because we have to use this equation, and we have to use the thing is like how to convert this into momentum equation, so that we can write total momentum change is 0. So how can we write that? Delta P for one toy equals to minus delta P for the other toy. So how can we do this thing? So I will include this in the notes, because right now I just forgot. Like how to go about this equation, because impulse of the applied by toy A and toy B is equal to impulse of toy B on toy A. So I'll include this in the notes, don't worry. Whenever you get the notes, so you will be able to do it. 9 marks for this, 6 marks. Again, oscillation question. Explain what is meant by simple harmonic motion. So simple harmonic motion in which acceleration is proportional to displacement,
and acts towards the equilibrium position.
but opposite to the equilibrium position. Yeah. So no, opposite to the displacement. So A equals. So you can write the equation also. A equals to minus W square x.
It should be force is proportional to distance from the equilibrium position.
Yeah.
Then
No.
force acts
Yeah.
towards.
Yeah, force is proportional to displacement, negative displacement, or acceleration is proportional to negative displacement. Let's see what definition do they use. Normally they use acceleration equation. They have not used the acceleration equation, but like direct to displacement from equilibrium position, so it is acceleration. So it's always acceleration. Rather than force, say acceleration. Use acceleration.
So they allow in terms of force, they said.
They did they allow? Yeah, in terms of force is allowed. So this is the acceleration time graph for the tire. Show that the amplitude of motion is about 0.5 meters. Easy question. So you have to use this W equals to 2 pi by F. So frequency of the tire is because this is 0.6 seconds, so this is for 2 waves, right? So this is for 2 waves, 0.6 second. You have to find for one wave, so it would be 0.3 seconds. So time period is 0.3 seconds. Then calculate the frequency, then calculate W, and then use acceleration equals to minus W square x. Acceleration is given, maximum acceleration is 2. Maximum acceleration is equal to minus W square x. So then you can use this formula to calculate the amplitude. A or X, same thing. Show that the amplitude of the motion is about 0.5 meters, this term. Calculate the maximum velocity of the tire. Maximum velocity is equals to plus minus omega A. So you can calculate. Draw a line on the graph to show how the velocity of the tire varies with time. So if the acceleration is given, so you can calculate the velocity. So you can draw the velocity time graph, because this is cosine graph, and you have to go back, right? So you have to find the acceleration velocity time graph. So velocity time graph, so you have to find the integration of cosine. Integration of cosine is sine. So you have to draw a sine graph. So this would be a sine graph. Same time period, it would be same time period, and just draw a sine graph. Bio students, math students can integrate this and draw the velocity time graph, because integration will give you a step back. Derivation will give you a step forward. So you want to go from acceleration to velocity, so you have to integrate this graph. So this is cosine graph. So integration of cosine is sine, right? So you have to draw a sine graph with same time period. The bio students, what you have to do is like see the gradient of the graph. So the acceleration is maximum. When the acceleration is maximum, so velocity would be 0. So you can start, obviously it would start from here, origin. Once you have got the clue, okay, it would start from origin, then you can draw the graph. Then it's easy, right? And when the acceleration is 0, velocity is maximum, right? Now you have to check that, do I have to find point up or down? Okay, so the velocity is maximum, but it is a descending line, so it is negative. Okay, so when the velocity is negative, like, so acceleration is so acceleration should be at the top. So acceleration is positive, just the opposite. So this point will come over here. So that's how you can draw these points. So it will take some time, but like you just go over the notes, you will find the answer. Probably last question. Drive this equation, so you can easily drive this equation. Nothing wrong with this thing. We are not supposed to use this formula. We are supposed to use the maximum velocity formula. It is a WA plus WA. So this is what you have to draw, a sine curve. You have to draw a sine curve. This is what you have to draw. Okay.
Yes.
This one with lower amplitude is not acceptable. This is wrong. The amplitude would remain same. Amplitude would remain same. No, amplitude
So it should
is
be
dropped.
the
Why?
velocity we calculated. So
No, why amplitude is dropped? Constant amplitude. Then they are saying, okay, any size is acceptable. Okay, so F equals to GMM over R square. So F equals to mg, and then this equal to this. So mm get cancelled. So G equal to this. So it's simple, right? 2 marks. This is on an astrophysics website. It states that for all satellites in a circular orbit, T square equal to R cube. This is Kepler's
Kepler's
law, where T is the period of the orbit and R is the radius of the orbit. Justify this statement.
So you
So
can
how
say
can you
md squared by r is equal to g.
Yeah, yes. You have to prove this formula. You have to prove this formula. That's how you can justify. You have to prove this formula. So this proof is given in the notes. So Gm over r square equals to centripetal force, or Gm over r square is the acceleration equals to rw square.